Similarly, if I give the second value of this, then it will be HG, and GH, and this is AB. So we are having AB here, and then the second value, and the second value is H minus G and AB here. So for this minus value, we are having HA plus GB. So this is HA plus GB, and here HA minus GA, and then we are having GA plus HB, and this is HB minus GB. Now there are some cancellations, so we are having HA cancel with this, G cancels with this, and we got that A is equal to minus B. And from here again the same, that HB cancel, GG cancel, and we got the same HA equals minus B. So our state 2 will come out to be, this is, our state is A, B, so A will come as A and B will come as minus A. And if I do normalize this one like this, then I will get that S2, again the normalization constant will be 1 over 2, and here I will get 1 minus 1, and this I will define as S minus. So this is for the minus value. So we got the two states. One is S plus, which is 1 square root 2, 1, 1, and the other state which is S minus, this is 1 over 2 and 1 minus 1. These are the eigenfunctions. These two are the eigenfunctions, and they correspond, these are the eigenfunctions, and they correspond to the eigenvalues, which are E equals H plus minus G. So we got the eigenfunctions is the eigenvalues. Now we will return to this relation, because we want to find S at t non-zero, means when t will be having some value. We got S plus and S minus here are S1 and S2. Now it's the time to find out the value of Cn. So the value of Cn, we will start that our system S starts at t equal to 0 in the state 1. This is given to us. So I can write this one state is 1, 0 is given to us there. 1 is 1, 0, which I can write is 1 over 2, 1, 1, and plus 1 over 2, 1 minus 1. If I add them up, I will get 1, 0. Now I can further write this thing is, I can write, if I take 1 over square root 2, I write this is square root 2 square root 2. So 1 square root 2 and 1 square root 2, and I write this is 1, 1, and then plus again 1 square root 2, 1 square root 2, and this I write is 1 minus 1. Then I know that this one is our S plus and this one is our S minus state. So in front of the state we are having the Cn. So this is our Cn, which is C1 or C plus due to S plus state, and this one is our C minus or C2. So we got our C1 is 1 over 2 and our C2 is 1 over 2. Because we are having only two states, so I can write that our Cn is equal to, so now for Cn I will have to put 1 over 2, and for S plus I will put one state, which is this one, and then for S minus I will have to put this state, and this will be multiplied with it. So En, for En I will put E1 and E2 values here. These are E1 and E2 values, and E1 value is H minus G and E2 value is H plus G. So I will put these values and then the states will also multiply. So I will get that S state is equal, if I take the 1 over 2 and 1 over 2, 1 over 2 from here and 1 over 2 from here, so it will become 1 over 2, and I take from the energy the h out of it, the exponential, so minus h, and this is I h and t over h bar. Note that this h is a constant here in our matrix, while the h bar is the reduced Planck constant, and this is multiplied with e to the power minus ig t over h bar plus e to the power plus igt over h bar, and here e to the power minus ig t over h bar minus e to the power plus igt over h bar. So this will come out to be the result, and then I can write this from the formula that cos of theta is ei theta plus e power minus I theta by 2, and similarly the sine is ei theta minus e minus I theta by 2i. We will get our final state S is equal to, we will utilize this 2 there, e minus I h t over h bar, and here I can write cos gt over h bar and minus I sine gt over h bar. So this is our final result, and this is a very crude model for neutrino oscillations. Neutrino oscillations crude model is this one. So this is our final result. So we got everything in this problem, the eigenfunctions, the eigenvalues, and the coefficient Cn. And we finally found a state when t is non-zero. At any time t, we got the solution. We now solve problem 3.22, and problem 3.22 is saying that consider three-dimensional vector space which is spanned by orthonormal basis set. So the orthonormal bases are 1, 2, 3, 1, 2, and 3, such that their linear combinations are given in terms of alpha, and this is equal to I times 1 minus 2 times 2 and minus I times 3, and beta is equal to I times 1 and 2 times 3. So this is one of the problem in the Derive notations. And what are actually the requirements? The very first requirement is that construct the bra notation beta. Beta is given in the kit, and convert this vector into bra vector. And first we will find out this thing, and as we know that beta is this, so by converting this into the bra vector, we will have to take the transpose and conjugate of it. So the very first one, we will have to construct beta like this. So from here to do this, this will be equal. We will have to take transpose of it and conjugate of it. So in the transpose, the 1 from the kit, it will go to the bra, similarly 3, while in the conjugate, I will change the sign. So it will become I and 1 plus 2 and 3. Now in part 2, we are asked to find out the inner product of beta with alpha. So I will have to write beta, which is minus I 1 plus 2 and 3. This is beta, and alpha from here is I1 minus 2 plus minus I3. So I will have to multiply this one. So iota will multiply with I, and it will become minus 1. So minus minus plus 1, and this one will multiply with that 1. Similarly, we will have minus I this with this. So I know that these are orthonormal bases. So 1 with 2 and 1 with 3 will give me 0. So we will have for the rest of the term equal to 0. Only 3 will give result, while this with 1 and 2 will give 0 due to the orthonormal nature of these. So we will have plus 2 here and minus I here, so it will become minus 2I and 3. So the orthonormal nature will make this thing equals to 1 and this equals to 1. So we are having 1 minus 2i. So the result is 1 minus 2i. Now, in the third, we are asked to find matrix element A11 and A12. Find the matrix element of A11 and A12 of the operator. The operator is A, which is defined as alpha and beta. So we will have to find all the matrices, all the matrix elements. A matrix is equal to A11 is we are having 3 orthonormal bases. So we will have 3 cross 3 matrix. So A11, A12, A13, similarly A21, A22, A23, A31, A32, and A33. This is the A matrix, and we will have to find all the matrix elements such that any matrix element Aij is equal to I and A and J. So the very first one, which is A11, it means from that relation that this will be 1A and 1, because G is also 1. So I can write that this is 1, and then A is alpha here and beta here and 1. So this one I will have to calculate, and this is equal to, first put the value 1 here, and then the matrix alpha in this form. So it is I1 and minus 2, 2. And then we are having for alpha, 1 remaining. So we are having minus I and 3. So this is 1 times alpha, and then put the value of beta. So beta here is this one, minus I1 and minus I1. So this one is like this, plus 2 and 3. So, and we are left with 1 here. Now we will have to multiply them. So here, when I will come out of this, we will get 1, 1. And 1 with 2 will give 0, with 3 will give 0. Similarly, minus I here, and this will multiply with 1, 1. So this will give minus I, this is 1, and minus I and 1, 1, while 3 with 1 will give 0. So we got I here, and this thing is equal to 1, this is equal to 1. We got I here and minus I here. So this is minus I square, and I square is minus 1. So we got the A11 element equal to 1, while A12 element is, from this relation, we will have 1 here, and then we will have the A matrix, the A operator here, which is alpha, and beta here, and then 2 here. So we will have to calculate this one, but let's come to beta, and beta here. So in beta over here, we are having 1 and 3 orthonormal bases only, while here beta is multiplied with 2 only. So it means that this value in this matrix is going to 0, and that's why A12 is equal to 0, and our matrices are actually here. For A11 we will get 1, so we are having 1 here, this one is 0, this one is 0, and A12 is 0, rest all are equal to 0. So our matrix A is actually equal to 1, 0, 0, 0, 0, 0, 0, 0. This is the required matrix which the problem is asking. Thank you.